Hello students, today we shall see diagonalization of a square matrix using similarity transformation. So first we see what is diagonalization of a matrix, square matrix rather. If a square matrix capital A of order n has n numbers of linearly independent eigenvectors, then a non-singular matrix capital P can be found such that P inverse AP is a diagonal matrix whose diagonal elements are eigenvalues of capital A, and capital P consists of column vectors which are eigenvectors of capital A, the matrix A. Another part also d to the power m, d means here P inverse AP, diagonal matrix. D to the power m, m is any positive integer, is equal to P inverse into A to the power m into P. The diagonal matrix P inverse AP is D, and if we raise it to the power m, positive integer m, then it is given by P inverse into A to the power m into P. Okay, and from this of course we can find A to the power m by pre-multiplying with P and post-multiplying with P inverse. In this result we shall see as a note at the end. A to the power m can be obtained. Okay, that is, this result helps us to find the integral power of a given square matrix easily. So let us prove the proposition for a square matrix of order 3, and then it can be generalized for square matrix of any order n. Okay, so let capital A be a square matrix of order 3, and let lambda 1, lambda 2, lambda 3 be the eigenvalues of capital A, and also let capital X1, capital X2, capital X3 be the corresponding eigenvectors. Lambda 1, lambda 2, lambda 3 are three eigenvalues of A, and capital X1, capital X2, capital X3. X1 consists of X1 and Z1, X2 is X2 Y2 Z2, X3 is X3 Y3 Z3. These three are the corresponding eigenvectors. That means X1 is eigenvector corresponding to lambda 1, X2 is eigenvector corresponding to lambda 2, X3 is eigenvector corresponding to lambda 3, so that these results are true. Ax1 equal to lambda 1 x1, Ax2 equal to lambda 2 x2, Ax3 equal to lambda 3 x3, and further these three eigenvectors are linearly independent. That is most important. X1, X2, X3 are linearly independent, so that if we construct a matrix capital P with these three eigenvectors as column vectors, capital P, x1, x2, x3 means x1 and z1, x2, y2, z2, x3, y3, z3. This is the matrix P formed with these three eigenvectors as column vectors. Then the rank of this matrix will be 3. Why? Because these three column vectors are linearly independent. So the determinant will not be 0. 3 by 3 determinant will not be 0, means this is the highest size square submatrix of P, and therefore rank is 3. In one way determinant not 0, that's why rank is 3, but in another way also we have defined the maximum number of linearly independent columns or maximum number of linearly independent rows gives the rank. So here these three columns are linearly independent column vectors, that's why rank of this matrix is 3, and therefore determinant is not 0, rank 3, determinant of P is not 0, so P inverse will exist, inverse of the matrix P will exist. Okay, now A into P, this given matrix A into this matrix P consisting of the eigenvectors is equal to A into this matrix x1, x2, x3, this matrix capital X1, x2, x3 column vectors. Now if we multiply this matrix by A, we get actually ax1, ax2, ax3. Okay, but ax1 equal to lambda 1 x1 because x1 is eigenvector corresponding to lambda 1. Similarly ax2 is lambda 2 x2, ax3 is lambda 3 x3. Okay, now this lambda 1 x1 gives us what? Because capital X1 is x1 and z1, so if I multiply here lambda, it will be lambda 1 x1, lambda 1, lambda 1 x1, lambda 1 y1, lambda 1 z1. If I multiply x2 with lambda 2, it will be lambda 2 x2, lambda 2 y2, lambda 2 z2. Similarly lambda 3 x3, lambda 3 y3, lambda 3 z3 will be coming. So we have written here lambda 1 x1 this column, lambda 2 x2 this column, lambda 3 x3 this column. Okay, now this matrix can be expressed as the product of two matrices. First matrix is P, means x1 and z1, x2 y2 z2, x3 y3 z3. P we have written whatever we have found, column matrix with eigenvectors, this P, into this diagonal matrix. This diagonal matrix is diagonally lambda 1, lambda 2, lambda 3, and all other elements are zeros. So if I multiply these two matrices, we shall get this. Here, of course, lambda 1 x1 can be written as x1 lambda 1. Lambda 1 is a scalar. You write in the beginning or at the end, no matter. So with this convention, this product of these two matrices is this matrix. You can see by the product rule of matrix. If we see x1 into lambda 1, we have written lambda 1 x1, okay, x2 into 0 by x3 into 0, so it is lambda 1 x1 simply. Similarly, x1 into 0, x2 into lambda 2 means it will be lambda 2 x2, x3 into 0. So second element we shall get. Third element similarly, x1 0, x2 0, x3 lambda 3 we have got. So similarly other elements. That means we have got P into D. This matrix let us name as D, diagonal matrix. It is a diagonal matrix, PD. So let us say PD. Therefore, what we have got? AP equal to PD. AP equal to PD. D is a diagonal matrix consisting of the eigenvalues of A. Now, pre-multiplying by P inverse this equality, P inverse AP will be P inverse PD, but P inverse P is I, unit matrix. So ID equal to D, identity matrix, unit matrix. So when we multiply the matrix remains same, ID. So what we have got? P inverse AP equal to D, where D is the diagonal matrix constituting of diagonal elements only with eigenvalues. So capital A is diagonalized. So this is the result we have proved for 3 by 3 matrix, and easily it can be extended to a case of square matrix of order n. So to diagonalize a matrix, we need to find eigenvalues, eigenvectors, and of course eigenvectors should be linearly independent and should be n in number for a square matrix of order n. So diagonalization done. Now second part, this result we have to prove d to the power m equal to p inverse a to the power m p. So d equal to p inverse a, we have proved. D means diagonal matrix. What we have got now? D square is d into d. So value of d substituted, p inverse a p, p inverse a p. Now if we multiply this p and p inverse first, matrix multiplication is associative. Anywhere you can give bracket. So p and p inverse if we consider first, so it will be p inverse is I. Okay, so p inverse ai ap. Now p inverse p is I, so ia or ai both will be a, means a into a we shall get. Ai is a, so a square. So what we have got? D square equal to p inverse s square p, means p inverse and p has no power, only a is raised to the power 2. So d square is p inverse s square p. Now if we want to find d cube, d into d square you can write, or d square into d you can write. So d into d square means p inverse ap, p inverse s square p. Now again if we consider this product p and p inverse first, so it will be I, then p inverse ai s square p, but ai is again a, so it is a s square. A s square is again a cube, so ultimately we get d cube equal to p inverse a cube p. Okay, and so on. In general, we shall get d to the power m equal to p inverse a to the power m into p for any positive integer m. So the result is proved. But another note I want to add, we have proved d to the power m is equal to p inverse a to the power mp, but our main aim is to find a to the power m. So if I multiply this d to the power m by p from the left and p inverse from the right, so right here also same operation, p and p inverse we have used. So p inverse is I, here p inverse is I, so I a to the power m I, but I a to the power m is a to the power m, and a to the power m into I is also a to the power m, so we get a to the power m. So what we have got? A to the power m equal to p d to the power m p inverse. Mth power of any square matrix A is equal to p into d to the power m into p inverse. P we know, d we know, diagonal matrix consisting of eigenvalues, but d to the power m, it can be easily seen that d to the power m will be just diagonal elements raised to the power m. You can see d square, d cube, etc. It will be obviously lambda 1 to the power m, lambda 2 to the power m, lambda 3 to the power m. So easily d to the power m can be obtained, and with the help of this we can find a to the power m. This is the main utility here. So let us say some examples on diagonalization. So diagonalize the following matrices using similarity transformation and also find a to the power 50. Okay, so first we do this smaller ones, that is a 2 by 2 matrix, Roman 1. First we find the eigenvalues. So for that we write characteristic equation of A is determinant of a minus lambda I equal to 0. So a minus lambda I, all of we know, we subtract lambda from the diagonal, 3 minus lambda, 6 minus lambda. Another 2 remains same, other elements remain same. So determine this equal to 0. If we expand, we get 3 minus lambda into 6 minus lambda minus 4, and simplifying what we get, lambda minus 2 into lambda minus 7 equal to 0 means lambda equal to 2 and 7. These two are the eigenvalues of capital A. So eigenvalues we have got. Now we want to find eigenvectors. So eigenvectors will contain two components. So eigenvectors capital X, let us denote by capital X, will consisting of this x and y, two unknown elements, unknown variables. So this capital X eigenvectors are non-zero solutions of this equation. All of we know a minus lambda I x equal to O. Capital X means this column vector and O means here null vector. So a minus lambda already we have. So this is a minus lambda I, and capital X means xy, and this 0 0 null vector. Now when lambda equal to 2, 2 and 7 are eigenvalues. So put lambda equal to 2 here, then we get 1 2 2 4. Now let us subtract 2 times first row from the second row, means we operate like this: r2 change to r2 minus 2 r1, elementary operation, so that the system, rather the coefficient matrix, becomes in echelon form. So the rank of this coefficient matrix is 1, and there are two variables, n is 2, so 2 minus 1 means 1. Only one linearly independent solution. For a homogeneous system, we know n minus r linearly independent solutions, so only one solution will be getting linearly independent, although it will have infinite number of solutions. So this system reduces to x plus 2y, 1 into x plus 2 into y equal to 0, x plus 2y 0. Now if we put x equal to 2 and y equal to minus 1, we get 0. This is a non-zero solution. So clearly x equal to 2, y equal to minus 1 is a non-zero solution. So the eigenvector corresponding to lambda equal to 2 is capital X1 is equal to the column vector consisting of 2 and minus 1. So this is the eigenvector corresponding to lambda equal to 2 we have got. Now when lambda equal to 7, if we put lambda equal to 7 here, it will be minus 4, it will be minus 1. So the system 1 becomes minus 4, 2 and 2 minus 1. Now again we use the elementary operation, r2 change to r2 plus half r1. So if we add, these two will be 0, means coefficient matrix again in echelon form, only one non-zero row, so rank is 1, so it will have only one Li solution. So this system 3 reduces to minus 4x plus 2y equal to 0, or 2x minus y equal to 0, cancelling minus 2. So clearly here x equal to 1 and y equal to 2 is a solution, non-zero solution. So the eigenvector corresponding to lambda equal to 7 is x2 equal to the column vector with 1 and 2. Okay, so you have got eigenvector corresponding to lambda equal to 7 also, means two eigenvectors. Now these two eigenvectors are linearly independent because lambda 1 lambda 2 are different eigenvalues. 2 and 7 are different eigenvalues, and already we know eigenvectors corresponding to distinct eigenvalues are linearly independent. And easily also it can be seen that x1 is 2 minus 1, x2 is 1 2. So x1 and x2, none is the scalar multiple of the other, so they are linearly independent. So let us form the matrix P with these two column vectors, capital X1 and X2. Capital X1 was this 2 and minus 1, and X2 is 1 and 2. So with this capital X1 and capital X2, capital X1 and capital X2, already we have seen in the theory. Here are two vectors. So P is this matrix with eigenvectors, maintaining the serial, of course, X1 and X2. And determinant of P is 5, obviously. 2 plus 2 into 2 plus 1 means 4 plus 1, 5. So non-zero, surely it will be non-zero, rank is 2. Now adjoint of this matrix P, adjoint P is cofactor of 2 is, this 2 is 2, and cofactor of 1 is minus 1, omitting these two, you get minus 1, and cofactor of this minus 1 is cofactor of this 1 will be this, and this omitted this, but it is in first or second column, so it will be plus 1. Similarly, cofactor of this minus 1 will be minus 1, and cofactor 2 will be again these two, and then we have taken transpose. Okay, so you have got the adjoint matrix this, and for a 2 by 2 matrix, easily adjoint can be remembered like that. Principal diagonal elements, we interchange the position, means these 2 and 2 same, so interchange position same, and other diagonal elements you just change the sign. This will be minus 1, this will be plus 1. So that's this way also we get adjoint of a 2 by 2 matrix easily. Main diagonal element interchange position, other diagonal element change the sign. So this is adjoint matrix P. Therefore P inverse is 1 by determinant of P into adjoint P. 1 by determinant of P is 5, 1 by 5, so 1 by 5 taken inside. This is the P inverse we've got. Now we shall see that P inverse AP will be surely diagonal matrix. with eigenvalues as diagonal elements. So P inverse AP. This is P inverse, this is A, this is P. So multiply first these two. 2 into 3 is 6, minus 1 into 2 minus 2, 6 minus 2 is 4. Yes, okay. Then 2 into 2 4, minus 1 into 6 minus 6, 4 minus 6 minus 2. Okay, correct. Then 1 into 2 3 plus 2 into 2 4 7. Okay. Then 1 into 2 2, 2 into 6 12, 14. Okay, so we have multiplied these two and got this matrix, and similarly we multiplied these two and got this 10 and 35 in the diagonal, and other two elements 0. You can see very easily. Now this 1 by 5 take inside, it will be 2 and 7. See, P inverse of P is 2 0 0 7, means diagonally 2 and 7. These are the eigenvalues, lambda 1 lambda 2 here, 2 and 7. So which is required diagonal matrix with eigenvalues of A as diagonal elements, which is similar to A. Means this matrix is similar to capital A, because this is similar to transformation. This P inverse AP is similar to A by definition. So this is the diagonal matrix similar to capital A. Now we want to find A to the power 50. So here D is P inverse AP. D means our diagonal matrix, and by the result already proved in the theory we have seen, D to the power 50 will be P inverse A to the power 50 P. D to the power 50 will be P inverse A to the power 50 into P. And from this we can get, just pre-multiplying by P and post-multiplying by P inverse, we shall get A to the power 50 equal to P into D to the power 50 into P inverse. So actually directly this line we can write. Directly this line, this is standard result, directly we can write this. Without showing these two lines, we can write A to the power 50 is this. Now value of P, D to the power 50. This is D. D to the power 50 will be just 2 to the power 50 and 7 to the power 50 diagonal elements raised to the power 50. Other elements remaining same. So now as before, we multiply these two first, get this 1 by 5 taken here scalar, and then these two we multiply and we have got this. This multiplication you will see. Okay. So this is A to the power 50. Instead of multiplying A into A 50 times, we have got this easily with the help of diagonalization of the matrix. So then let us see Roman 3, example Roman 3, Roman 2 left as an exercise. So here A is this matrix. So characteristic equation is determinant of A minus lambda is 0. So diagonally minus 2 minus lambda, 3 minus lambda, 3 minus lambda we have written, and then expanded. There are two zeros in the third column. So let us expand in terms of third column. So it will be 0 minus 0 plus 3 minus lambda into these two element multiplied. These two element if we multiply, it will be minus common. Here minus common means lambda plus 2 into lambda minus 3, and then minus 4 into 1 means plus 4 will be coming. So simplifying, we have got lambda minus 3, lambda plus 1, lambda minus 2 equal to 0. So from this we get lambda equal to minus 1 from this, lambda equal to 2 from this factor, lambda equal to 3 from this factor. Means lambda values are minus 1, 2 and 3, which are the eigenvalues of capital A. Eigenvalues, 3 distinct eigenvalues. So there will be 3 distinct eigenvectors also. Now eigenvectors are non-zero solution vectors of this equation. A minus lambda I x equal to O. O means a null vector. So a minus lambda I we have already, this is a minus lambda I, and x, capital X means here a column vector with 3 components x, y, z. Let us write. So let us find the eigenvectors corresponding to lambda equal to minus 1 first. So when lambda equal to minus 1, put here lambda equal to minus 1, get this matrix. Okay. So let us solve this system. Now to convert the coefficient matrix to echelon form, we interchange first the first row and third row, so that one is coming here in the first position, so interchanged, and then let us use this operation. Third row change to third row minus 1/4 of second row, so that this both the elements will be simultaneously 0. Okay, so 1/4 will be minus 1 and this will be 1. So if we subtract, we shall get both the elements 0, and then we shall change the second row. Second row change to second row plus 4 times first row, so that of course 16 will be coming here. So we have got this. So this coefficient matrix is in echelon form with 2 non-zero rows. So rank is 2. This is system is homogeneous. So the coefficient matrix is now in echelon form and its rank is r equal to 2. So the system will have n minus r linearly independent solutions. N minus r, n means number of variables here, n. 3 minus 2 means 1. So only one linearly independent solution will be there. Although the system will have infinite number of solutions, but only one linearly independent solution. Means only one eigenvector we are getting. Now the system 2, whatever written, reduces to this system, and if we write the individual equations again, what you get, 1 into x plus 0 into y plus 4 into z equal to 0, means x plus 4 z equal to 0, and 0 into x plus 4 into y plus 16 into z equal to 0, means 4y plus 16 z equal to 0. So from this we get y plus 4 z equal to 0. 3 and 4 are marked. So we have to write a non-zero solution of these two simultaneous equations 3 and 4. So if we take x and y both 4 and z equal to minus 1, we get both the equations satisfied. So 4 4 minus 1, x4 y4 z equal to minus 1 is a non-zero solution. You can take in your own way the values. We take the simple values. So 4 4 minus 1 is a non-zero solution, so that the eigenvector corresponding to lambda equal to minus 1 is capital X1. Let us name as 4 4 minus 1, column vector consisting of these three components 4 4 minus 1. Okay. Now when lambda equal to 2, another eigenvector, this system number 1, we shall put lambda equal to 2 here. It will be minus 4 1 1 diagonally, another element remaining same. So when lambda equal to 2, number 1, system 1 becomes this. Now again we make the operation first row and third row interchange, because if we use these two rows, two elements will be simultaneously 0. So let us keep the 0 rows in the bottom, that's why. So 1 0 1 in the first row, and then first row comes to the position of third row. Now we operate R3, row 3 change to row 3 minus row 2. So the both the elements will be 0, and then row 2 change to row 2 plus 4 times row 1. Okay. So we get this matrix. So this is in echelon form. The coefficient matrix is now in echelon form, and its rank is 2 because there are two non-zero rows. So this system will have, as before, n minus r. 3 minus 2 means only one linearly independent solution. Only one linearly independent solution, n minus r. And the system reduces to system number 5. We have named it 5. So this will reduces to this, means again individual equations we write x plus z equal to 0 and y plus 4z equal to 0. So here if we take x equal to 1, z equal to minus 1, first equation is satisfied, means number 6 is satisfied. And if I take z equal to minus 1, then I am to take y equal to 4. So 4 minus 4 0. So 1 4 minus 1 is a non-zero solution. Therefore eigenvector corresponding to lambda equal to 2 is capital X2 vector 1 4 minus 1. Okay. Now last one, when lambda equal to 3, the system 1, already we have lambda equal to 3. If we put here, it will be minus 5 0 0. Okay. Other things remaining same. So when lambda equal to 3, the system 1 becomes this. Now again we interchange first row and third row. We get 1 here, and then we operate second row plus 4 times first row, third row plus 5 times first row. So we get this matrix. Now if we interchange first row and second row, the 0 rows to be in the bottom. So we get third row, second row, and third row means R3 R2 with double row symbol. So we have got this matrix. This is in echelon form. Coefficient matrix is in echelon form, and rank is 2 obviously. And so the system will have n minus r means 3 minus 2, 1 Li solution as before, only one Li solution. And the system reduces to 1x 0y 0z, means only x equal to 0, 0x 1y 0z equal to 0, means y equal to 0, but z is, third equation is eliminated, means z can take any value. 0x 0y 0z equal to 0 means z can take any value. X and y are 0, so let us take the simple value z equal to 1. So x0 y0 z1 means 0 0 1 is a non-zero solution, and this is the eigenvector corresponding to lambda equal to 3. So let us name this eigenvector x3 as 0 0 1. Now we construct the matrix capital P with the three eigenvectors capital X1, capital X2, capital X3, first, second, third serial. So P is the matrix consisting of eigenvectors, three eigenvectors, column vectors. So 4 4 minus 1, 1 4 minus 1, 0 0 1. So this is our P. Now determinant of P we have found. This is as usual 0 0 1 third column. So let us expand in terms of elements of third column. So 0 minus 0 plus 1 into 16 minus 4 means 12. Determinant not 0. Rank is 3. Surely capital X1, X2, X3 are linearly independent. Now matrix of cofactors. This is P. Matrix of cofactors of the matrix P. Let us find. So cofactor of 4 will be 4 into 1 minus 0 means 4. Then cofactor of this minus 1 will start with minus 1 because it is first or second column. So it will start with minus sign, and then omitting this column and this row, 4 into 4, 1 4 minus 0 means 4, but already minus 1 is there. And cofactor of this 0 will be starting with plus sign because it is first or third column. So omitting this row, this column, we shall get 4 into minus 1 minus 4 into minus 1 is 0. So 0. Similarly, other cofactors here also, cofactor of these 4 will be starting with the minus sign because it is second row first column. Second row first column, that's why. And omitting this and that, we get 1 minus 0, 1, and already there is a minus sign. Similarly, cofactor of this 4 will be second row second column, so it will be starting with plus sign. So 4 into 1 minus 1 into 0, so only 4. Cofactor of this will be starting with minus sign. This row, this column, omitting, we get 4 into minus 1 plus 1, and that is minus 3, but already there is a minus sign because of second or third column, so it will be 3. Similarly, other cofactors of this we have written here. Okay, so this is matrix of cofactors. Therefore, P inverse is 1 by determinant of P into adjoint P. So adjoint P means transpose of this matrix. So this matrix 4 minus 4 0 was row. Now we shall write it as column. Minus 1 4 3 row, we have written it as column. 0 0 12 row, we have written it as column. So this is adjoint P, and this is 1 by determinant of P. So this is our P inverse. Now P inverse A, let us find first. P inverse A, this is P inverse, this is A. A we have already in the question, so we have substituted. Now as usual, we multiply with this row and column process. So first into first plus second into second plus third into third, like that. So detail everything is shown here. Multiplication, matrix multiplication, we have got this matrix. You will check. Now this is P inverse A. Now P inverse AP. So this is P inverse A, and then P is, this matrix is A and this matrix is P. So okay, P we have got here. This 4 minus 4 0 minus 1 4 3 0 0 12 we have taken. P inverse A P. P inverse A we have calculated. This is P. This is P. P, where is P? This is P. Not this is P. This is actually matrix of cofactor. This is adjoint matrix. So this is P. 4 1 0 4 4 0 minus 1 1. We have substituted here. So P inverse A, this matrix, and this is P. Now we multiply as usual. Just one element I show. This is where minus 4 into 4 minus 16, 1 into 4 plus 4, 0 into minus 1. So this element. Similarly, first row, second column, first row, third column, all details are shown. So this is a diagonal matrix, and this 1 by 12, if we take inside, it is the diagonal matrix consisting of diagonal elements minus 1, 2, 3. And P inverse AP, we usually name it D. Diagonal matrix D. So this is the required diagonal matrix with eigenvalues. See, minus 1, 2, 3 were the eigenvalues, and they are in the diagonal, principal diagonal elements. So this is the required diagonal matrix with eigenvalues of A as diagonal elements, which is similar to capital A. This D, P inverse AP, is similar to capital A by definition. So this D is similar to A. So we have proved P inverse AP equal to D, diagonal matrix consisting of eigenvalues as diagonal elements. Now A to the power 50 we want to find. So this line, we know D to the power 50 is P inverse A to the power 50 P, and from this, if we multiply by P and here P inverse, we shall get A to the power 50 will be P D to the power 50 P inverse. So directly we can write this line as question demands A to the power 50. So this is the standard result. Now value of P substituted, D to the power 50. This is D. So D to the power 50 will be just minus 1 to the power 50, means it will be 1 even number, and 2 to the power 50, 3 to the power 50, other elements will be same as 0. So D to the power 50 written. This is P inverse. Now multiply first this 2, 4 into, it is actually 1 plus 1 into 0 plus 0 into 0, means we shall get only 4. Second element will be 4 into 0 plus 1 into 2 to the power 50 plus 0 into 0, means 2 to the power 50, and third element will be 4 into 0, 1 into 0, 0 into this, means it will be 0. So similarly other elements are also written, and 1 by 12 is there, scalar, and this is, these two we have multiplied first, got this matrix. Now again if we multiply again with this row column process, 4 into 4 16, 2 to the power 50 into minus 4, but minus 4, this 4 can be written as 2 square, so we have written 16 minus 2 to the power 52, and then 0 into 0 0. Then if we go to the second column, it will be 4 into minus 1 minus 4, 2 to the power 50 into 4 means 2 square, 2 to the power 52. Okay, and third element is 3 into 0 0. So similarly if we go to the third column with first row 4 into 0, 2 to the 50 into 0, 0 into 0, 0. So similarly other elements are also multiplied and we have got this. So what we have got? A to the power 50 easily we have got without multiplying a 50 times. We have got a to the power 50. This is the utility. So this is diagonalization of a square matrix using similarity transformation, and this is the end of the topic linear algebra. Okay, thank you.